Hello and welcome to this clip going through finding the order of reaction by graphical methods. It's a slightly different technique to my other level questions on rates, except that this time you're using a graph and the shape of that graph to determine the order and other aspects of the reaction. So, looking through it, it gives you a reaction at the top. And it explains that a student investigates the rate of the reaction by monitoring the concentration of bromine over time. It also says that the student uses a large excess of HCOOH to ensure that the order with respect to HCOOH will be effectively zero. So the first thing to look at is the fact that it says that the large excess of HCOOH, methanoic acid, means that the order with respect to that particular compound is effectively zero. So even though it's actually reacting and in the equation, because there's a lot of it present, the concentration of it actually doesn't really change that much. So the fact that it's relatively constant in concentration means that, in effect, that makes it zero order. So to get the initial rate of reaction, we can find that from the taking a gradient at time equals 0 seconds and then working that gradient out. Now, because it says that your answer must show full working using the graph, that means that you'd have to work out the rate constant using a graphical method as well. So if you remember, that's your log to the base e, or natural log of 2 over the half-life. So let's start by taking our tangent at time equals 0. So the initial rate, like we said, is going to be dy over dx. So that gives us 4.5 times 10 to the minus 5 moles per decimeter to the minus 3 second to the minus 1. So obviously your gradient, if you were to try this question out, would be slightly different to mine. So usually a sensible range is allowed to compensate for this. So let's now go on to working out the rate constant. Now there's two possible methods that would both mean using the graph. You could either do half-life and use the first method we talked about a bit earlier, or you could work out that the rate equation is going to be K times the concentration of Br2. Not forgetting that we've discounted HCOOH because it was made to be effectively zero order. So let's do the half-life first, and then we'll do the other method after. So taking the half-life at 190 seconds, there's probably again a bit of flexibility either way here because you're reading off a graph. Dividing the natural log of 2 by 190, that gives you 3.648 times 10 to the minus 3 second to the minus 1. So just a quick clarification at the bottom right-hand corner of the screen on where the unit came from. Obviously, you would cancel out moles per decimeter to the minus 3 on the top and bottom of the expression. So now let's do it as if we were just using concentration of Br2. So I'm going to use the initial concentration and the initial rate and substitute into this expression. So if we now insert the values 4.5 times 10 to the power of minus 5 divided by 0.010, we get 4.5 times 10 to the minus 3 seconds to the minus 1 as our value. So this would be using the value for the rate of reaction at t equals 0 that we worked out earlier, and also the concentration of bromine at t equals 0, which is 0.010. So this takes us to the end of this review of how you might want to approach a level question on rates and graphical methods. But thanks for listening. I hope it's been useful, and until next time, see you soon.